All right, we've got some more sample problems here looking at solutions where I have a strong acid and a strong base. So strong versus strong. First thing I want to look at, because every one of these units is in milliliters, and we've been using milliliters and converting them to liters, but our numbers are getting pretty small when we were looking at moles and which one was the limiting reactant. So I just want to remind you, I think we talked about it, where we know that molarity, capital M, is equal to moles per liter, but that's also equal to millimoles over milliliters. So I'm going to use these units on these examples just to kind of show you how it's a little bit easier and it's a little less decimal places. So we have HBr titrated with NaOH. So I'm just going to write our reaction here. We have HBr plus NaOH, and this double replacement reaction is going to happen. We're going to have water and NaBr. So we know when we have strong versus strong that 100% of these reactants are dissociating. So we do not have to worry about Ka constants. We're just going to take the negative log, and we know that whichever one is the excess. So for example, if the acid is in excess, then we will just do the negative log of that for the pH. But if the hydroxide is in excess, we would still do the negative log of that, but that would give us our hydroxide concentration. So we would need to do 14 minus that to get our pH. So let's look at an example. We have 20 milliliters of 0.2 molar HBr. So 20 milliliters, 0.2 molar. And then we have 0.2 molar NaOH, 0.2 molar. Calculate the pH after 15 milliliters of base. So all of these volumes are base. So we're told 15 milliliters. So let's look and see what we got here. To find out how many millimoles, right, we can just do our volume, our 20 milliliters times 0.2 molar to give us 4 millimoles. And remember, I told you molarity, yes, is moles per liter, but we can also do millimoles divided by milliliters to get capital M. So 4 divided by 20, if I show you the opposite, millimoles divided by milliliters, 4 divided by 20 is 0.2 molarity. So we'll just use that. This will be easier to work with than 0.004. And here, let's find out how much NaOH we have. So we're just going to do 15 times 0.2, and we have 3 millimoles. So we can see here that my hydroxide is my limiting reactant. I only have 3 millimoles as opposed to 4. So when this reaction happens, I use up my NaOH. And I have 1 millimole of HBr left over, which is our H plus concentration. Now, we want, in order to find the pH, we need to do the negative log of the concentration. Well, I have 1 millimole, but how much volume is there? Well, there's a combined 20 plus 15, so 35 milliliters. So 1 millimole divided by 35 milliliters should give me my concentration. 1 divided by 35, we get 0.02857. That's my concentration for my H plus. Now I need to do the negative log of that. So negative log of my answer to get a pH of 1.54 units. So it is very acidic, which is that 1 millimole of HBr left over. Now let's look at it. What if I went from 15 mils of base to 19.9 milliliters of base? So let's look at this example. I'm just going to draw a line separating this. It's the same reaction, so I'm just going to use the same columns. So I still have 20 milliliters and 0.2 molar, and I still have 4 millimoles. The only thing that's changing is my quantity of base, 19.9 milliliters. It's still 0.2 molar. So let's see what that gets us. 19.9 times 0.2. I have 3.98 millimoles. So I can see that I still have NaOH as my limiting reactant, right? Because if I minus 3.98, I have none of that left over, minus 3.98. I have 0.02 millimoles of acid left over. So let's see, 0.02 millimoles of my H plus over, what's my total volume? 20 plus 19.9, so it'd be 39.9 milliliters. I can find this concentration, millimoles divided by milliliters. So 0.02 divided by 39.9, 5.0123 times 10 to the negative fourth. So let's take the negative log of that, answer, and I get a pH of 3.2999, so pH of 3.30 units. So the pH is definitely less acidic than before when I had 1 millimole for 35 milliliters. Here I have 0.02 millimoles for almost 40 milliliters. So pH went up. What about if I go up to 20 milliliters? So from 19.9 to 20, when we have equal amounts of that acid and base. Let's try that example. So we've got 20 milliliters of 0.2 molar and 20 milliliters of 0.2 molar. Let's see what we get when we figure out millimoles. Oh, it's going to be 4. There we go. 4 millimoles here, 4 millimoles there. So obviously I'm going to subtract 4 because that gets both of these to 0. That means that I have no excess reactant. So both of them consumed equally. That means that there is no competing hydronium ions or hydroxide ions. We know that the products that are formed, water and the salt, that there's no hydrolysis happening, that both of these have strong parents, right? And because of that, when I have equal amounts of both, that my pH is exactly 7.00. Let's look at the next one. So I went 19.9 to 20. Let's look up at 20.1 and see what that does. So again, I've got the same amount of acid, 20 milliliters, 0.2 molar, gives us 4 millimoles. Here I've got 20.1 milliliters, 0.2 molar. Let's see what that gets us. 20.1 times 0.2, 4.02. So we can see here, my limiting reactant is going to be my acid, minus 4. So I will have no acid left over, minus 4. I'll have 0.02 millimole of my hydroxide, my base left over. So if I look at having 0.02 millimole of my hydroxide over 20 plus 20.1 is 40.1 milliliters. Let's see what this concentration is. 0.02 divided by 40.1. I get a concentration of 4.9875 times 10 to the negative fourth. Let's take the negative log of my answer. Now remember, to take the negative log of that, I'll take this as negative log, that gives me my POH. So 3.30211 is my POH, because we're looking at this concentration of hydroxide. To get pH, I need to do 14 minus that answer. So I get 10.697, so 10.70. All right, last one on this page, 31 milliliters. So again, we've got the same for our acid, 20 milliliters, 0.2 molar, so 4 millimoles. And here I have 31 milliliters, 0.2 molar. So 31 times 0.2 is 6.2 millimoles. Obviously, my acid will get used up. Minus 4, so I'll have 2.2 millimoles of my hydroxide left over. Then if I find the concentration of this, so 2.2 millimoles over total volume, so 31 plus 20, 51 milliliters. So 2.2 divided by 51, you get a concentration of 0.0431. And that's again for my hydroxide ion concentration. So let's do the negative log of that. That would be my POH. And then 14 minus our POH to get our pH, 12.63. A very basic solution on a scale of the pH range of up to 14 and 12.63, very basic. So those previous problems are all strong acid, strong base. These next ones, we're looking at acetic acid, so a weak acid with NaOH, so a strong base. Now, if we write this out and we take acetic acid, which is HC2H3O2 plus NaOH, we're going to get HOH, water, and sodium acetate. Now we also know that sodium hydroxide, since it's strong, that there's no hydrolyzing happening, but we have our weak acid that will hydrolyze. So over here, when I have my sodium acetate, we can split this apart. We will have our C2H3O2 undergo hydrolysis. But let's write down what we know first to get started. We have 35 milliliters of our sample of 0.15 molar of our acid. And we have 0, this is all of our base volumes. We have 0 milliliters of NaOH, and it's also 0.15 molar. So because I have 0 moles of it, since I have 0 milliliters of it, this first one is all about looking at just our acetic acid, finding the pH of the acetic acid. Well, we know that acetate, well, let's look at our acid here. Our acid going HC2H3O2 is going to form an equilibrium where I have H plus ions and my acetate, C2H3O2 minus. And therefore, we're going to look up our Ka value for acetic acid, looking at Appendix D. Our Ka is 1.8 times 10 to the negative fifth. And if I form that equilibrium, our ice chart, and I make my H plus and my acetate both X, I started with 0.15 moles of this. Technically, this would be 0.15 minus X, and these would be plus X plus X. We'll check our 5% rule, though, in just a second. So let's solve for our H plus, and then we can take the negative log of it to get the pH of our acetic acid. So if I do x squared, my products over my reactants, 0.15 equal to 1.8 times 10 to the negative 5. Let's do some calculator crunching. 1.8 times 10 to the negative 5 times 0.15, and then square root my answer. I get x equal to 0.001643. Remember, this is my H plus concentration. Let's double check and make sure we're within that 5%. So our x over our initial, so divided by 0.15, and then times it by 100. Oh yeah, we're at 1.09% ionized, so that's great. We're under the 5% rule. Now, since I have my concentration, let's just take the negative log of our H plus, 0.001643. We get a pH of 2.78 units. So our pH here, and that was just a simple Ka problem. I was given 0 moles of sodium hydroxide, so I had to find the pH of my acetic acid. And we knew that my acetic acid has a Ka value because it's a weak acid. So we could just look at its hydrolyzed dissociated ions over molecular concentration. So x squared over 0.15 equal to my Ka. Pull out x and take the negative log of x.